Had to wind up a dirt road on a mountain to get to it. It was really fun going down the mountain and getting to like the turnaround. Sticking it or not. When I got there, it's like, oh.
This car?
Yeah, that's definitely some money. It's uphill on the way in, and it's usually better. Because on the way back, you just relax and enjoy.
I don't know, enjoy the walk down. In reality, I just need to get in better shape and I would have been fine, but
That helps.
Good morning.
Well,
Malia?
yeah. So I mean, like running on the
So you're the only one that did not do. Which actually is not the big deal. There's an option. We're probably yeah, for sure. You're the only one that did. Like, everyone but you did it. It's probably gonna. 6 to 7. Here.
Here?
Yeah, it'll be here.
I just like, I work till 5 and I won't be like back till 5:30.
Sure, a few minutes late. I was gonna say, because you already have a problem. There may be an option. I don't know. If
you gotta be sure.
6, 7, that we get.
Yeah.
They have an option to check station at the actual client, like,
Okay.
which is that's what let you cut out.
Might be free that Saturday. So that'd be next weekend.
Yes.
So the training would be like next week.
Would be Wednesday. And if you can't, even if you can't make the training, you just gotta go to the check station for an hour. He'll walk you through it.
I know I don't work on this Saturday, but if you come.
Well, and so what we'll do is, maybe we'll try to line that out, because it's not that far away, so it's, you know where the starts now. Okay, so if you go.
I'm from Ohio.
So if you go out 64 towards about even Shelby yet, just basically drive south about 18 miles. There's a giant lake down there, and they have a WMA on that lake patrol hunt that weekend. So there's oh, absolutely. Yeah, no, I'm not just be like, just show up over there. No, it'll be like, here's where you're going with an address, and this is what you're looking for, and this is what you're doing.
Okay, yeah, then I can actually remember that say that this.
We'll make it. I think that, so if that doesn't work, for whatever reason, there's probably more opportunities to get.
I think that would work out, because I work like every other Saturday, but like, that's the Saturday I go to work, so.
All right, we'll try and make it happen. Okay. Yep. Good morning, everybody. How are we doing? We have a good fall break. Yes. Did anybody do anything overly exciting?
I went hiking on George on trail. I haven't done it before.
Well, that's good. Very good.
Absolutely nothing.
That's disappointing. So, well, that's all better. I spent the entire fall break in bed with the stomach bugs, so you guys all win there. So for those of you that signed up for the extra credit for the CWD sampling, it looks like Wednesday was it 6 to 7? The training will be here, so Wednesday the 3rd. I'm waiting on Fish and Wildlife to give the final okay on that. But in which case, just show up to the building. It should be about an hour long. And then at that point, we'll try to assign you where you're going. Other than that, I will not be here on Tuesday. Kate Williams, my grad student who's doing the elk research, is going to give you a lecture on wildlife diseases. That'll be the last thing included on the test on November 9th. We will have a review session on Thursday, the 4th, just like we did the last time. Okay. Hopefully that'll go through any of the potential problems, questions you have, a little bit more practice on the math. This is going to be a lot more math heavy, a lot less definitions and memorization. You will have the formula sheet that's up on Canvas right now as part of your test, so you don't have to memorize the formulas. You do have to know how to use them. Okay. I think this test will actually probably be easier than the last one. Make sure you have the ability to calculate some way, shape, or form. I have on the test day, I got pulled into an administrative issue. So my other grad student, Nate Hooven, who was the TA for this class last year, is going to administer the test. Okay. Anybody have any questions? No? You're all seem quiet today. So this is the last major component of math that you will basically do for this class. And it's another population estimation, density estimation technique. This is a fairly common and applied. So unlike the capture recapture stuff, where what you guys worked on is pretty basic and things have grown a lot. This is still fairly basic, but the methodology is such that it's still applied pretty regularly in research today. So it's a nice thing for you to be aware of. And that really is the use of line transects and distance sampling is really what it is. And its application into understanding how many animals are present within an area. And the entire idea is that you're going to survey a set location, a defined area, in a manner that allows you to determine and account for all variation in space and habitat, climate, to understand what the population of a species is or group of species. So you're not going to do a census, right? You can't, it's very impractical to try to walk every bit of an area, especially when you start talking about large scale space. So this is trying to account for that using a sampling protocol. So the estimate's based on a sampled count, given that protocol. It basically means you're doing a little bit less work, but a little bit more math, because it is an estimate. So you have to come up with some kind of confidence interval and understanding of what you're actually capturing and what potential variation there could be based on your methodologies. It's used a lot more with mid-sized animals, things like deer, elk, bighorn sheep, goats, in this fashion. It's also used a lot with grassland birds, just because of the amount of space in a grassland where birds can kind of move around quite a bit. Whereas things like forest songbirds, usually they use a slight variation of this, which is a point count, okay, or a plot count. Ideally, this method actually disturbs the animals a little bit less than going out and catching them. It also is a little bit less disturbing than trying to census them all, where you're potentially trying to either mark them or deal with all the variation spatially so much that you have to chase them back and forth multiple times. So it has its value. Like everything in wildlife methodologies, there's usually a trade-off. It has its positives, it also has some negatives. Determining the variation and what you can actually calculate out in a system can be difficult, but usually we can figure it out over time. So the main difference between a line transect and a plot or a point count is the transect, they're both, set amount of space for most things, where, you're walking a transect that's 200 meters, or you're sampling a plot. So the forestry students can speak to this quite a bit, where you're measuring, trees, saplings, all within a certain radius. So you have a given space. You're hoping that that space is representative of the entire landscape, or you need to do that over and over and over again until you actually have enough of them that it is a representative sample of the entire study area. If that's done correctly, then you can extrapolate that data to come up with an estimate of what's going on in the study area. Now, the catch with the plots versus the transects really comes down to a plot is generally a lot smaller. And therefore, if you're dealing with whether it's plant species or animal species, if they're at incredibly low densities, you may need to sample a lot more space to actually detect them. Okay, so transects allow you to sample that space with some speed versus the plots that are a little bit more localized. Now, plots are actually probably a little bit more accurate because you're dealing with a smaller area, you're able to get better data and make sure that data is more precise. So when you're dealing with animals that are high density, not only because of data quality, but speed, you're able to deal with it a little bit more efficiently via the plot method. Usually with point counts and transects, you're looking at a detection rate for a species or a landscape variable, plant, pellet groups of about 20% to 80% to have effective understanding with math. Okay. Now, there are some assumptions that go along with this, right? A model is only as good as the assumptions behind it. And some of the basic ones are if you're, whether it's a transect or a plot, at the point of the plot or on the actual line that you are following, whatever you're looking for, it is assumed that if it is at that location, on that transect immediately, or in that point, you have 100% probability of seeing it, detecting it. So no missing it. For the transects, okay, because as we're going to see here in a second, you're going to do some measurements once you detect that animal. You are assuming that you're actually detecting that animal at its original place. So they are not moving before they're detected. And in addition to that, if you're walking a transect and you see a turkey, you take your measurements and you walk another 50 meters and you see another turkey, you really hope that that's not the same turkey that's going back and forth. Otherwise, you're double counting. Okay, so that's one that sometimes is risky, and it depends on how you have the transect set up. You have to then, as you're collecting that data, be able to accurately take distances and angles, because that's going to factor into your detection probability along the transect, which that seems really basic, and it should be. but try getting a bearing on a bighorn sheep running up a cliffside. And just try as it's going, you know, that's kind of the thought, is it's sometimes a lot harder than you think. And this kind of goes along the whole recite as well, where the animals are not, they're existing in the landscape as they would normally exist, and there's no reason that their behavior or detection is altered or attractiveness to each other, okay? We good on those assumptions? So we have two types of transect surveys. You will be responsible for being able to calculate the fixed width. Now, just like we talked about with the mark recapture, improvements happen. Math and abilities to calculate variables allow us to increase our efficiency and precision and estimates, or precision of our estimates. So this is the initial model. And basically what it is you have a transect that's a set length, and you are using a set width on each side of that transect to survey. That is the amount of area and space you are surveying. You have a known area, and that's all you care about. You walk that transect, you notice you notice what you're looking for, you take your measurements, you're good. So you know what you can actually detect in here, and you assume that you're basically getting almost all of it. Now, the width of that transect is usually based on the habitat you were sampling and your effectiveness at detecting said animal within that width. So you want to increase your likelihood, so it's almost 100% that if it occurs in this space, you will see it and be able to measure it. Does that make sense? Once you see an animal, what you're actually collecting, right, in general, what you care about, A, is the number of animals you see, the distance from where you are in the transect to where you see that animal, okay? This can be referred to as the RI for radius, right? Or sometimes it appears as D for distance. The angle here. And then you also need to understand your total transect length and then what you were surveying in terms of width. So W, which is both sides, so it's ×2. Okay. And what you're gonna end up doing is calculating that theta in degrees. Okay, so that you can get a distance from the line here. Because this is actually what you're caring about. You're just getting at it through, what's that math called that you probably had in freshman year of high school? Trig. I don't know. That's when I don't know when I had trig actually. I was thinking geometry, but yeah. All right. So we get all that information. So we want to know what the density of a species is using this method. So we are going to walk a transect that's 1,000 meters long. The width of that transect that we're surveying is 20 meters on each side. We saw 15 grouse. We flushed 15 grouse, and that's what we're looking for. However, only 12 of them actually occurred within that transect. What is our density in hectares? I don't see everybody getting their phone out to do the calculation, so this is good. That's me asking you to see if you can solve the problem. This is what you're going to have to do on the test.
grouse per hectare?
Yes, it is. Yeah, you got it. Anybody else everybody else get that? That did it? So what you end up doing, you end up getting point like 0.00003, 0.0000, yeah, 3. And then you have to convert it up to hectares. Okay, because everything you did here is in meters. Does that make sense? Anyone have any problems with that? Is this way more straightforward and easy? Yes, right? Yeah.
So what was the point of the angles and stuff?
We're getting there. We're getting there. So that's the initial one. Now, the improvement. Okay, and this is where those angles come in. So we actually flushed 15 grouse, right? But we could only include 12 in the survey. So we just lost data. We lost that as part of our estimate. And people started noticing that. So they were like, okay, so there's got to be a way that we can get an accurate estimate without losing that data, because all that's important. And you know, it comes down to just understanding what our actual survey area is so that we can extrapolate. Well, if we can figure out what our detection probability for an animal is based on its distance from the transect, then we can include everything we saw, because we're making a calculation to where that animal is in relation to the transect. Right? So that basically means you're taking away the W component, and you're only utilizing a transect length. Somewhat. So you still have a terminal width that you can detect species. So what you're basically doing is, instead of saying, oh, I think it's 20 meters, I'm going to let the math tell me what my actual width is, because at some point, right, you're going to have animals out here that you're not going to detect. So we can estimate the probability of detecting the animal based on its distance from the transect, and use that to tell us what our effective survey area was. Does that make sense? Okay. And all of that is based on knowing the distance to the transect when we flush or see an animal. All right. This is all based on the idea that your ability to detect the species has some predictable or mathematical function based on the distance from your transect line. And once again, we have to maintain that assumption that if it is on the line, there's no possible way we can miss it. So that you're always starting at a distance 0. So this is your detection function for a set data set. Distance 0 is always at 100% detection. The math won't work. If this is at 75%, the math doesn't work. It's gone. The model falls apart. All right. We're just, the big thing is that it allows us the ability to use statistics to tell us what our actual feasible detection ability is. And how that comes in handy is there's a lot of individual variation between our surveyors. Okay. So Eldine and I go walking in the woods. He may be better at seeing deer than I am, but I may be better at seeing deer poop than he is. And insert anything else you want. So if you have the assumption that every individual has the ability to see things the same way, you're going to basically get inaccurate data. What we can do with this method and using math is we can actually come up with detection curves and corrections for every individual that surveys, or every species and every habitat that we survey. That allows us to take that variation and eat it up and give us a more accurate estimate of populations. And also comes up with that confidence interval, so a gauge on our accuracy. None of that will be on the test because the function curves and everything else get very complicated very quickly. But your first job, if you're doing this as a biologist, is you collect that data and then you must come up with this detection curve, because this is what's used to correct your estimate. So how does that look if you're trying to start applying that? Well, it's pretty easy once you have the detection curve, because all you're doing is taking that slope, which is what you're really using, that slope of that curve, and inserting it into the formula to come up with a way to correct your potential for missing detections. Okay, so this is where you incorporate that mean of right angle distances. So that's where it goes off of that measurement. Your overall length of transects there, your estimate on your detection probability, and then your number C. This is not on the test. But do you guys get a good idea how that's incorporated? Or at least somewhat see how it's incorporated? At least understand why we're incorporating it? How you kind of determine your K is through this formula. So this is what the probability of detection is, what you're kind of coming up with here. And you're using the maximum distance that you can detect that animal, okay? With the thought being that this is probably the maximum you could have ever detected that animal. And then using that, so this is not the distance, the straight line distance to the transect, but it's the distance that you saw it. So that RI, that's what this is, okay? This is the measurement from that line. Because you have to be able to correct for the fact that the animal can see you and react to you. And that's where that whole assumption that you're seeing the animal first, where it's supposed to be. So you could have an RI value that's 200 meters long because you see an animal at the end of the transect, standing on the transect from where you're starting the transect, if your transect's 200 meters. So that would be a value, so it's 200 meters, but it's technically 0 meters from the transect, is what that would be. Okay, so it just allows you to correct for how far off it is. Does that make sense? And then you're solving through to get to your K value, and then there's an ugly formula you guys probably don't want to calculate, and that's okay. But general rule here is when that K is 1, that means you have an equal probability of detection. Greater than 1, which is the most common, you get that slope. That's problematic because that means your sighting at 0 is not actually happening. Okay? Questions on that? You guys feel comfortable enough that you want to include that on the test? No? Okay, you are paying attention. Good. All right. So how that might be applied for our grouse example. Here's a survey, total linear transect length, 10,000, 178 with a mean of 18.93 distance. Turns out our K was 3.44. That's that detection curve, right? So it's above 1. So the further they get away, the less likely we are to detect it. That's good. That works out that you have 2.48 grouse per hectare instead of 3. Okay. That was a very short lecture today. That's it. That's all. we can use this opportunity to go over other stuff. I didn't want to go into all the math because you guys seem pretty freaked out by all the math. Do you want to use this to go over any previous questions? Problems with the last lectures? I figured that we're going to have enough on the test that I didn't need to overload things because the disease section, Kate's going to have quite a bit on there that you're going to need to digest. Okay. Well, yeah.
Maybe like just examples for math questions.
I will try to have something up on Tuesday and we'll try to go through them on Thursday. All right. I have no daycare on Tuesday, so that's why we switched the times. So yeah, I'll try to have things posted on Tuesday. I am waiting to get some questions from Kate on her lecture that she wants to use, and I will make sure that you all have an understanding of what she's going to give you at that point. Anything else? Yes.
In this example, you would have to round up to 3 graphs anyway, so.
Well, so this is a density estimate, so you don't, right? So it's not an actual population count. It's a, how many graphs do you think per acre? Other questions? So we still use this methodology. Like I had 2 grad students that use this methodology for their master's projects. So it's pretty applicable to a lot of things right now. Dr. Price has used it for, I think, his snake work. You know, we use it for elk sightings, elk population estimates. So yeah, still use it for, who helped out with the grouse surveys? Any of you? Did you go after the grouse surveys? So this is basically what you're doing, right? So yeah. Yeah, it doesn't necessarily mean you have to see the animal. You could just hear it as long as you can get. Yeah, so hold on. One of the other ways that get commonly applied is with the point sampling. We can still do this with point sampling, but what usually happens is you have a point, right? So say this is a person in the woods. The assumption is that at this point, it's 100%, right? Well, it gets difficult for things like songbirds, right, that are this big, 80 feet up in the canopy full of leaves. How do you get a measurement of distance to that animal? Can you? No, right? So what you tend to do is the assumption is that we're still able to detect everything at 100% at this point in space. Because the birds are singing, you can hear, the hope is you hear everything. Well, if you're doing it auditory detection, then you have to worry about things that could affect your ability to hear, right? So foliage is one of them, wind is another, rain, all background noises. So what happens is, because you can't measure to a certain place, what bird researchers do and bird biologists do is they'll make this, so they go to their point and they basically have this data sheet collection that this will be like 0 to 20 or meters, 20 to 40, and 40 to 60. With the thought being that they can accurately, so say they hear a cardinal. Well, they'll put themselves and they'll have, you know, some compass, right? So north. They'll have some bearing on what's going on. And what they'll do is they'll go, okay, I think that cardinal is from here, it's north, and it's about 35. They'll actually put a point in space in their data sheet where they think that animal is. And they'll use that to calculate the distance, the RI. And what they can do is, if things are fuzzy, they'll go to a categorical distance detection. So they'll just lump it, and it doesn't give you as nice of a curve, but it still gives you a K value that you can use. Continuous distance gives you a better curve and a better K value. But if you're uncomfortable with your ability to do that, you can put them in zones. Cool? Make sense? Trying to think of other times you could do that. That's a good example. We use, so the application to just estimating distance is there, but we'll do that also. We'll use similar ideas in terms of trapping grids. So say this is your point that you're trapping. You can actually lay out like a spider web of traps within that area, of Sherman traps, so small mammal traps. And since you have a known space that you're trapping, you can actually determine a density of small mammals in that space based on how many mammals you're catching in this grid, in this locale, and how does that dissipate as you get away from it. That's how you can get a population estimate for small mammals and density. Because trying to walk along a transect and counting mice and they run, good luck. Okay. Oh, good. You're shaking your head. None of that is going to be on the test, but you can at least see how it's very applicable to what we do in terms of management. Other questions? We can do this with vegetation as well, in terms of looking for plants or looking at habitat characteristics, stem densities, and so on. Species densities. For, say you want to increase hard mass or soft mass, you want more certain trees, you can look at where they occur. How do you apply a management strategy, and does that then responsive? All right, all good? I kept you for another 5 minutes, I'm sorry. I'll see you all on, well, I won't see you until Thursday of next week. Yep.